this video, we're going to work through the steps identified in the PowerPoint presentation on the process of obtaining and analysing Sentinel-2 imagery to produce information on wildfire burning. We're going to look at an example from the Evia region in Greece, which we can see here on Google Maps, just northeast of Athens. The wildfire events we're going to look at occurred between mid-July and mid-August 2016. The first thing to do is search for these wildfire events on the European Forest Fire Information System, or EFIS. We can zoom into the area of interest, which in this case is the municipality of Karistos in the Evia region in Greece. It's here now. We can turn on the burned areas identified by the visible infrared imaging radiometer suite sensor and the moderate resolution imaging spectral radiometer sensor. We can see there are a number of burned areas identified by these two sensors, and we can use the information tool to look at some of the details for these areas. We'll take a closer look at them now. Okay, so we can see that the large burnt area to the south was recorded on the 25th of July 2016. And we'll have a look at the burnt area just in the northwest, which we can see now was recorded on the 13th of August 2016. So these various burnt areas identified in this municipality are the ones that we want to locate and analyse using Sentinel-2 data. To access the relevant data, we open up the Sentinel Scientific Data Hub and log in. Once logged in, we can zoom to the area of interest. Now, using the tools available, we can draw a bounding box around the area that we want to find an image for. In the search box, we can type in Sentinel-2 and then press enter. This will bring up a large amount of results, so we can run an advanced search to specify a date range. We click on the Sentinel-2 mission and then scroll up to input our appropriate date range. We know that we want an image sometime after the 13th of August, so we can specify a date range from, say, the 14th of August until the 30th of August. Once we press the enter button, a few options should come up. We can examine each image by looking at its footprint. Here we can see it come up on the map, and we can also click on the eye to look at the product details. If we scroll down a little bit, we can see some information about the image, for example the date and time of acquisition and the size of the file. The image we're looking at is from the 29th of August, and we can see that the file size is 5.67 gigabytes. If we click on product, we can scroll down a little more and find out some more information about the image, for example the pass direction and the processing level. Once we're happy that this image meets our requirements, we can click on the download product button to download the data. This process can take quite a long time depending on the speed of your internet connection and other factors. The next step is to open the product in the Sentinel Snap toolbox. The file needs to be unzipped before it can be opened. In the toolbox, we go to File, Open Product, and search for the XML file in the unzipped folder. In the window that opens, we need to specify the correct UTM zone for the area we want to look at. In this case, it's UTM zone 35N. At this stage, if we try to open a full RGB image, it may take quite a while to process. Ideally, what we want to do is create a subset image, as this will massively cut down on processing time and make it far easier to export the image and open it in other GIS systems. To create a subset, all the bands have to have an equivalent pixel resolution. Therefore, we have to resample some of the bands, preferably to 10 megapixel resolution. To do this, we go to Raster, Geometric Operations, and Resampling. Under the Resampling Parameters tab, look at the option by reference band from source product. We need to choose one of the 10 meter resolution bands as a source band to resample from. We'll choose B2 here. The upsampling method can also be changed if necessary, but we'll leave it as nearest for this example. We can run the process now, and when it's done, a temporary product will have been created in the Product Explorer. The next thing to do is to define an area of interest to create a subset from. A quick way to do this is to open one of the individual bands as a grayscale image, as this process is fairly quick. Now we can zoom to our area of interest. When we're satisfied that it's correct, we can go to raster and subset. Now we can define the bands we want to create a subset from. For our purposes, we're going to select bands 2, 3, 4, 8, 11 and 12. Click OK and this will create a temporary 6-band subset image. We can open up a color image now with far less processing time. To do this, we right click on the subset product and select Open RGB Image window. We select the bands we want to display through each color gun and then open the image. Further processing can now be carried out in the toolbox, but my personal preference at this point is to export the subset image and carry out further image processing in QGIS. To export the subset, we simply go to File, Export, and choose GeoTIFF BigTIFF as the format. At this point, we have a workable subset image. However, the process has taken quite a long time and requires quite a lot of storage space. If we need a few images, this process can take a very long time and can cause storage problems and potentially lead to data download restrictions. There is, however, an alternative method we can use for accessing and downloading Sentinel-2 data, which circumvents many of these problems and inconveniences. We can download the data in JPEG 2000 or JP2 format from the Amazon S3 window. We need to type in the following address: sentinel-pds.s3-website.eu-central.1.amazonaws.com. This brings us to the Amazon S3 site for accessing Sentinel-2 data. If we scroll down, we come to the Sentinel image browser. The green tiles we see are the image footprints, and we can also see there is a bar to specify the date range and also the cloud coverage percentage. Now we're going to zoom into our area of interest in Greece. We can define the date range. Since we know the image we're looking for is from the 29th of August, we can narrow the date range appropriately. We can leave the cloud coverage percentage range between 0 and 10. Now we can click on one of the tiles that has come up, and we can see it's the same one we downloaded from the Scientific Hub previously. Some details about the image show up. If we click on Link to Tile Data, this opens a new window with a list of the 13 individual Sentinel-2 bands. One of the advantages of using the Amazon S3 site is that we only have to download the bands that we want. When we click on band 2, it begins to download, and we can see that the size of the file is only 95 megabytes. The process can then be repeated for the other bands. The metadata can also be downloaded if necessary in XML format, and a cloud mask is also available to download in GML format. We're now ready to begin to create a multispectral image from the individual bands downloaded. We're going to use QGIS to do this. As with the process in the Sentinel Snap toolbox, we have to resample bands 11 and 12 to the same pixel resolution as the 10 meter bands. As we can see, the JP2 images are already loaded into the layers panel in QGIS. We can double click on one of the 10 meter bands and then go into the General tab. We can see that the number of pixels per column and per row are specified. We need to take note of these figures, as this is what we'll use to resample bands 11 and 12. Now we go to raster, then projections and warp. We can specify the input file as band 11 and specify an appropriate output file. Note that the output file won't be in JP2 format, it'll be in GeoTIFF format. Finally, we need to enable the resize function and change the values for width and height to the values noted earlier. In this case, we change both the width and height to 10,980. This will resample the pixels in band 11 to the same size as those in the 10 meter bands. Now we run the process and we can repeat it for band 12 too. At this stage, we need to merge all our bands into one layer to form a multispectral image. However, we have some bands in JP2 format and 2 bands in GeoTIFF format. We need to change bands 2, 3, 4 and 8 into GeoTIFF format. We can go to raster, miscellaneous and merge, and then choose bands 2, 3, 4 and 8 in this order, which is very important, and then check the layer stack box, and then we can click OK. This will give us a 4-band multispectral GeoTIFF image, and we can repeat this process to merge bands 11 and 12 also, which will give us the 6-band multispectral GeoTIFF image. At this point, it's probably desirable to create a subset image. As discussed earlier, a subset image will cut down on future processing time and make it easier to visually enhance the image. We zoom into our area of interest. Again, it's the municipality of Karastos. And once we're satisfied with this area, we just right-click on the layer and then choose Save As. All we have to do now is select the option Map View Extent, and this will save a subset image of our area of interest. Now that we have our 6-band subset image, our aim is ultimately to try to manipulate the image in such a way that the features we are looking for, the burnt areas, show up as clearly as possible so we can delineate them and analyze them. We have a true color image open on the screen, and we can alter it by applying a histogram stretch to improve the visual characteristics of the image. In QGIS, there are a few predefined histogram stretches that can be applied, such as a cumulative cut stretch or a local histogram stretch. You can also manually change the histograms for individual bands, and this is a useful feature, but for now we will just apply a cumulative cut stretch to our true color image. Already the image appears far more visually appealing and offers more information. If we look closely, we can begin to make out some of our suspected burnt areas. They appear to be showing up a shade of grey or brown, as we can see here. If we recall from the EFIS system, there should be approximately 4 burnt areas from the last 2 months or so in this region. We can just about make them out here, here, a larger area in the south, and one more area in the northeast. The 2 shortwave infrared bands can be very useful for picking up burnt areas. I'm going to apply a band combination with Sentinel-2 which is a shortwave infrared band centered around a frequency of 2.19 micrometers, displayed through the red color gun, the near infrared band displayed through the green color gun, and the green band displayed through the blue color gun. If we apply a suitable histogram stretch to the resulting image, now we can see all 4 burnt areas showing up very clearly. They are all showing up a very distinct shade of red. Already we have some very useful and accurate information on the extent and location of the burnt areas. One thing to note at this point is that there are some areas obscured by cloud and partially obscured by cloud shadow in the image. For example, if we look at the large burnt area to the south, we can see that there is some cloud cover and shadow potentially obscuring part of the burned area. If we wish to do any further processing of the image at this stage, we run the risk of misclassifying these areas or having these areas adversely affect some of the data we produce. One way of dealing with such cloud cover is to try to remove these areas from the image using the ESA cloud mask provided in GML format with Sentinel-2 Level 1C products. QGIS will open GML files. When we've loaded in the cloud mask and projected it appropriately, we can see the clouds picked out by the mask. For example, it picks out the cloud we were previously examining around the burnt area in the south. However, we can also notice that there are various clouds not picked up by the cloud mask, and neither is the shadow. This is obviously an issue for the accuracy and extent of the process of masking out clouds, and various other algorithms for identifying clouds could be developed and applied to the image. For the purposes of this example, we'll continue using the ESA cloud mask to clip the image. It may be desirable to also mask out the water areas of the image. We can use a vector file of the administrative boundaries to do this, and we can remove the clouds from the new mask. To do this, we go to Vector, then Geoprocessing Tools, and then Difference. We can define the administrative boundaries as the input layer and the cloud mask as the difference layer. We can see the result once the process has been run. The clouds have been removed from the boundaries layer. Now finally, we can use this layer to clip the raster image, removing the water areas and clouds identified by the ESA mask all in one go. We go to raster, then extraction, and then clipper. We specify the appropriate input file and output file, and then select mask layer, and choose the new administrative boundaries layer. We can see that the result of this process is an image with the sea and clouds removed. Finally, for now, we can apply a normalized burn ratio to the image. This is a formula which can potentially help identify burnt areas in a multispectral image. In QGIS, we can apply this ratio by opening the raster calculator and inputting the formula. The formula for the normalized burn ratio in Sentinel-2 is the near infrared band 8 minus the shortwave infrared band 12 divided by the near infrared band 8 plus the shortwave infrared band 12. The result is a single band grayscale ratio image with pixel values ranging somewhere between -1 and +1. The burnt areas are clearly darker than most other areas in the image, and therefore we'd expect the pixel values here to be lower. We can use the Identify tool to get an idea of the range of values in the burnt areas. As we can see, there are many values appearing which range between about -0.2 and -0.35. If we inspect other values in the image, we see they are generally higher. We can try to determine a threshold for burnt areas at this stage and reclassify the image very simply based on this threshold. For this example, we're going to place all pixels with a value lower than -0.16 into one class representing burnt areas. A very simple way of doing this for visual purposes is just to go to the Style tab for the layer and select single band pseudo color rather than single band grey. Now we choose an appropriate color ramp and select Classify to classify the pixels in the image into 5 classes. We can amend the values automatically used for the classes, such that our lowest class includes all pixels with a value lower than -0.16. Once we've applied this, we can see that this is a very simple method for visually delineating the burnt areas. They appear in red, clearly distinguishable from the remaining areas in the image. This hopefully serves as a useful example for how burnt areas can be identified and visually enhanced to serve many of the purposes outlined in the initial part of the presentation.